Welcome to Yatim Khana and Madrasa Anjuman Khairul Islam's Pune College of Art, Science and Commerce, Camp Pune 1. Myself, Dr. Arif Tamboli, working as Associate Professor in the Department of Electronic Science. Dear students, today we are going to study about the operational amplifier. Operational amplifier is very important IC and it is having thousands of applications. So in today's lecture, we are going to study symbol of OpAmp, block diagram of OpAmp, then single power supply OpAmp, dual power supply OpAmp, then parameters of the OpAmp. There are various parameters related to the OpAmp according to which the selection of operational amplifier is done. Working of operational amplifier in open loop gain and in closed loop gain. Then in OpAmp there is one concept which is called virtual ground and real ground. All these things which we are going to study in today's lecture. So let us start from the introduction to operational amplifier IC. There are various types of the ICs available in the market for operational amplifier, but most widely used is operational amplifier IC number 741. So this is a 8-pin IC. So you can see over here, out of that 8 pin, one pin is not connected only, which is not used at all. Pin number 1 is used for offset null. Pin number 2 is inverting input marked by the minus sign. That is, symbol of the op-amp is always shown as a triangle. All of you know that. Pin number 3 is non-inverting input pin marked by the plus sign. Pin number 4 is for minus power supply in case of op-amp 741. Because OpAmp 741 works on dual power supply in the range of plus minus 9 volt to plus minus 18 volt. Pin number 5 is called offset null again. So pin number 1 and 5 you see over here. We are going to study this in detail, how to go for offset null. Pin number 6 is called as output pin. Pin number 7 is the power supply of the IC plus VCC, and pin number 8 is not connected. So to balance the symmetry, 4 pins on the left hand side, 4 pins on the right hand side. That is why this IC is a 8 pin. So all of you know that now. The triangle is the symbol of operational amplifier, whatever its number. This is the actually how does the IC looks. Normally we show the symbol as a triangle, but actually how does the IC looks. You can see here IC741. It is a LM series CN, 4 pins on this side, 4 pin on that side. Now I have one more diagram in which again it is clear that this is the symbol of the op-amp as a triangle, inverting input pin marked by the minus sign, non-inverting input pin marked by the plus sign, and this is the output. So in this diagram, here plus VCC supply 7 is not shown, here minus VE supply is not shown, and this is the picture of again your IC. Now let us go to the block diagram of operational amplifier. Triangle is a symbol for operational amplifier, and in that triangle symbol normally we indicate the input marked by the negative sign, which is called inverting input. We indicate the another input marked by the positive sign, which is called non-inverting input. We do indicate the output, and thereafter we indicate only plus VCC and minus VE. In case of operational amplifier IC741, dual supply is recommended by the manufacturer in the range of plus minus 9 volt to plus minus 18 volt. Now, what are the different blocks inside the operational amplifier? So there are 4 blocks inside the operational amplifier. First block is called input stage, and name of that circuit is dual input balanced output differential amplifier. Second block is called intermediate stage. This is called dual input unbalanced output differential amplifier. So if you look at the first block, it is having 2 input as well as 2 output. Therefore, dual input balanced output differential amplifier is also called as double-ended input, double-ended output differential amplifier. Look at the second block, which is called intermediate state. Dual input unbalanced output differential amplifier. So here there are 2 inputs, but output is only 1. And from here onwards, inside the op-amp, the journey of single-ended output starts. So this block is having input as a double-ended, but the output is single-ended. Next block is called level shifting stage. It is also called as constant current source block. And the last block is called output stage, which is called push pull amplifier. And in this way, by combining all these four blocks, the circuit inside the operational amplifier is fabricated. Let us go to the dual power supply concept. What do you mean by dual power supply? So dual power supply is a very simple concept. Two batteries if you have, each of 9 volts say, what you have to do, one battery is having two terminals, namely plus and minus. Another battery is also having two terminals, namely plus and minus. So you do the connection such that negative of first battery is connected to the positive of battery, and that junction is declared as a ground pin. Left hand side battery positive terminal is called plus 9 volt because it is a 9 volt battery, and it is also called as plus VCC. So we are going to see what do you mean by VCC. The right hand side battery, left right hand side batteries, this terminal which is negative terminal is called as minus V, and it is a minus 9 volt. So this is a very simple concept of the dual power supply. Now instead of showing always the batteries like this, we show the symbol of the battery, and you'll understand that this is also one of the way to represent. We have a battery here. They have shown a multi-cell battery. So like this, B1 of 9 volt plus and minus. Then again there is one more battery B2 plus and minus. So multi-cell battery they have shown. Junction of the two batteries, namely B1 and B2, is declared as a ground. Upper terminal red plus 9 volt, lower terminal minus 9 volt. And this power supply is used for operational amplifier as a dual power supply. It starts from plus minus 9 volt to plus minus 18 volt in case of IC741. But it goes in the interval of plus minus 9 volt, then plus minus 12 volt, then plus minus 15 volt, and plus minus 18 volt. Now let us go to the connections. We have a dual power supply with three terminal, namely one is plus VCC. So it will come pin number 7, minus VE will come to the pin number 4, and ground is declared as a ground. Now if you look at the OpAmp 741, you will find out that there is no ground pin directly connected to the operational amplifier. So that also you can notice from the beginning. I have shown you this diagram. So here can you see, this is a plus VCC, this is minus V, inverting input, non-inverting input, output. This pin is not connected. Pin number 1 and 5 are the for output offset null. So there is no direct ground pin for the OpAmp 741, and this is the beauty of the OpAmp 741. So the question comes then, how does the circuit gets completed even though there is no direct pin? So look at this. Whenever you apply the non-inverting input as a plus here or inverting input as a minus here, in OpAmp we apply either input at the non-inverting input terminal. At that time non-inverting input is grounded, or we apply the input at inverting input terminal. At that time non-inverting is grounded, or we do apply the input at both inputs, and that input applied is always with respect to ground, and output is also measured with respect to ground. So you see here, this output at a pin number 6 is measured with respect to ground. Input is applied here, green, with respect to ground. Input is applied with respect to ground, and in this way the path becomes closed. So this is the reason why there is no direct pin of ground for operational amplifier IC741. Now there is one more way to understand dual power supply. Instead of showing the 9 volt, we have taken here 15 volt, one battery, 15 volt, another battery, two batteries junction declared as a ground point. This is plus VCC will go to positive voltage of the op-amp. This is minus V will go to the minus voltage of the op-amp, and there will be the input. So this is for simple understandings. Now it is not necessary that operational amplifier IC must have a dual power supply. In market there are operational amplifier ICs which work on single power supply also. So look at this diagram. Here it is plus VCC and here it is a ground. Here there is no minus V because this operational amplifier works on single power supply, means plus 5 volt, plus 10 volt, plus 12 volt, only one battery will require. But the input stages are same. input circuitry is the same. Input circuitry is not going to change. There are 4 blocks inside the op-amp, or 4 block requires power supply. So the same case is for dual power supply. All 4 blocks requires dual power supply. Here all 4 block will require single power supply. Input stage, dual input, balanced output, differential amplifier. Intermediate stage, dual input, unbalanced output, differential amplifier. Third one is the level shifting stage, which is called constant current source. Last one is called output amplifier. So in this way, the 4 blocks are common. Inverting input is applied to the first stage. Non-inverting input is applied also to the first stage. So first stage is having 2 input and 2 output. So dual input, balanced output. Second stage, 2 input, 1 output. So from second stage onwards, the journey for single-ended output starts. So in this way here, second stage is dual input, unbalanced output DA. In this way, this is this thing. Now example of this IC is what? So here again there are 4 blocks and their names are here. So you can go through this. It's very simple. So first block, which we called as dual input balanced output DA. What is dual input balanced output DA? So dual input balanced output DA is an electronic circuit which is having namely 2 inputs V1 and V2. Normally V1 is applied at inverting input, V2 is applied at non-inverting input. Output is taken from collector of each transistor, and these two outputs are called double-ended output. There is RE and there is VE. In this diagram, RC1 and RC2 are not shown, but which has to be shown. But here it is actually replaced by a current mirror. So it is not shown over here. So no problem. Here, same R1 and R2 are shown. Means this R1 is nothing but RC1 collector resistor of transistor T1. R2 is nothing but collector resistor of transistor T2. So this is very important, R1 and R2. So they are in the form of current mirror. So this is plus VCC, this is minus VE. Here it is inverting input, here it is a non-inverting input. Because in this diagram, you will not understand how does this input comes from here, because for op-amp as a triangle, we mark both input from left hand side and output is from right hand side. Output is the last block's output, means our amplifier's output. So now let us go to this. Here you can understand these are the 2 inputs. This is the output of first block. This is the first block which is called dual input balanced output differential amplifier. Now let us go to the next block, which is called dual input unbalanced output. So output is taken from collector of transistor T2 only. 2 inputs are there. So this will come from here, then jumper and here. So input 1 and input 2 from left hand side and like that. Last block inside the op-amp is complementary symmetry amplifier. Complementary symmetry amplifier. So actually the last block of the op-amp is amplifier, and in that amplifier 2 transistors are used, namely NPN and PNP. Now this is a block diagram of complementary symmetry amplifier, in which you will feel that from where this comes, source voltage. So here we have shown this source voltage which is connected externally to this, but inside the op-amp this source voltage is the output of third block, because this is the last block, fourth block. So output of third block is what? Constant current source. So let us go again to the block diagram very fast. So here level shifting stage or constant current source. So this output is given to the amplifier. So this is the output amplifier, and which type of amplifier is used? Complementary symmetry amplifier. So circuit is somewhat like that. So like this, and this output is the output taken from pin number 6 of the op-amp. So that is called single-ended output. So operational amplifier IC is having only one pin, that is pin number 6 in case of IC741, that is called single-ended output. So this output is always measured with reference to the ground, and the ground you know very well, 2 batteries are connected in series and junction of the 2 batteries is declared as a ground. With reference to that ground, this output is measured. So in this way, in case of operational amplifier, the last block, which is called complementary symmetry amplifier. Now what is the function of these 2 transistors? So function of these 2 transistors for op-amp, if you are applying AC voltage which is having positive half cycle as well as negative half cycle, so NPN transistor will amplify positive half cycle, PNP will amplify negative half cycle. And if you are applying DC, Then both the transistors work together and amplify the DC voltage. So in the next block, I will show you that detail. Yes. Complementary symmetry class B push-pull amplifier has acceptable linearity for some applications. Now see here, this again I am showing you that this is the input sine wave which is from third block, and third block is the constant current source, or it is also called as level shifting stage. So here positive half cycle and negative half cycle are shown respectively by red color and blue color. And NPN transistor is again marked by the red color. So positive half cycle is amplified by NPN transistor, negative half cycle is amplified by PNP transistor. And in this way, these two transistors combining together will work as amplifier in the last block of the operational amplifier IC. And this is the final output of IC741, that is pin number 6. Now after understanding all these blocks, there is equivalent circuit diagram of OpAmp. Equivalent circuit diagram of OpAmp. What is the equivalent circuit diagram? Equivalent circuit diagram of the OpAmp is in between inverting input and non-inverting input. In between inverting input and non-inverting input, input resistance is offered by the OpAmp, means first block of the OpAmp, that is called dual input balanced output differential amplifier, and that input resistance is marked by the Rin. Then last block of the op-amp you know very well, that is amplifier. So amplifier is as good as source of voltage. So this source of voltage is marked as a plus and minus. And Rout is the output resistance offered by the op-amp. So that is called Rout. So this is called as equivalent circuit diagram of op-amp, which is having input resistance Rin offered by the op-amp for an input signal, namely applied at inverting and non-inverting, and this resistance is offered by the first block of the op-amp. Rout is offered by the last block of the op-amp, and last block is the amplifier, so it is a source of voltage, and somewhat like this, this is the equivalent circuit diagram. Again, there is one more equivalent circuit diagram. You can say here A into VD. A means gain, VD differential voltage, R0 means Rout resistance, input resistance Rin, and this is the very simple understanding equivalent circuit diagram of operational amplifier. Now let us go to the 4 stages one by one. What is the input stage? The main function of operational amplifier is, at first it creates a difference between the two input signals and then amplifies the differentiated signal. So in the input stage, the differential amplifier creates the difference. In this stage, differential amplifier also provides the high input resistance which is necessary for the operational amplifier. You can see in this stage the dual input balanced output differential amplifier is used, which increases the voltage for the next stage operation. Its input and output is double-ended. So this is the information about input stage. What does it consist? Dual input, balanced output, differential amplifier. What is its function? Its function to amplify the difference between the two inputs and pass to the second stage. What is its role? To offer the input resistance. Next, intermediate stage. What is the intermediate stage? The output of the input stage, that is the first stage, is used as the input of the intermediate stage. So first stage output is used as the input to the next stage. In this stage, the direct coupling happens. So in this stage, the DC voltage is greater than the ground potential, that is 0 volt. Its output is double-ended and its input is double-ended and output is single-ended. So here onwards the journey for single-ended output starts. So its input is double-ended and output is single-ended. So this is the intermediate stage. Next one, level shifting stage. It is also called as constant current source. So in this stage shifting of the voltage level happens, that is why it is called level shifting stage. Then output stage. In this stage, push-pull amplifier is used, which we have already studied. You can read through this information. Then next, some operational amplifiers are specified as requiring for positive and negative power supply, and some, as I told you, it doesn't require dual power supply, it requires only single power supply. Now, what is the example of single power supply IC? The example is LM324, and this LM324 works on single power supply, but manufacturer also suggests you can apply dual power supply also. So LM324 is plus minus 5 volt or only plus 5 volt. So both options are available. But in LM324, you have four ICs or four operational amplifiers in one IC only. So this is the LM324. 1, 2, 3, 4 op-amp. Inverting input, non-inverting input, and output. Like that, the configuration for each. So for one op-amp, 3 terminals, 2 input, 1 output. So 12 terminals are there and 2 terminal for supply. So it is a 14-pin IC, and you can see here how does LM324N works. Here 1, 2, 3, 4, 5, 6, 7, and on that side 7, 14 pin. So this is the LM324. One more IC available in the market for op-amp. There are two operational amplifiers present in one IC only. So here one and here one. So one op-amp will require 2 input, 1 output, 3 terminal. Another will be 3 total 6 and 2 terminals for power supply. So here you can say plus VCC plus V and ground. So this works on single power supply only. So like that, here there are various types of the op-amps. Applications. There are various applications of the op-amp. Op-amp is used in various electronic circuits. So you can read all these informations as and when you have the time. You can watch the video again and again, and you can go through this. Now we are going to proceed for the basic functioning of the op-amp. Op-amp's first stage, what it does, it amplifies the difference between two and produces the result at the output. Now, in case of op-amp, the input V1 is normally applied at inverting input. Input V2 is applied at non-inverting input, and plus VCC supply and minus VE supply. In case of op-amp, whenever voltage at inverting input pin V1 is greater than voltage at non-inverting input pin, the op-amp output is in LVL. And whenever voltage at non-inverting input pin means plus is greater than voltage at inverting pin, the output op-amp is in HVL. So here I have shown that representation with the help of both diagram. So first of all, what I said you, in case of op-amp, whenever voltage at inverting pin minus pin, suppose V1 is 5 volt, is greater than the voltage at non-inverting input pin. So here the voltage at negative pin is greater than the voltage at positive pin. In that case, the output of the op-amp is forced into LVL, low voltage level, and this LVL is very much equal to minus VE. Means suppose minus VE is equal to minus 9 volt, then whatever the difference, irrespective of the difference between the two input, output is forced to go to LVL. Remember here when we ask the question, what if V1 is 5 volt, if V2 is 2 volt, what is the V out? Student answer 5 minus 2, 3. No. Operational amplifier here is not used as a subtractor. It is used as comparator, and it is open loop comparator. So in this case here, the difference between two input is amplified whenever V1 applied at negative terminal is greater than V2 applied at positive terminal, means non-inverting input terminal. At that time, the output is forced into LVL. And here V1 is 2 volt, V2 is 4 volt. So which voltage is greater? Voltage at non-inverting terminal, positive terminal is greater than voltage at inverting terminal. Therefore, output of the op-amp will force to HVL. HVL means high voltage level, and this is equal to plus VCC. Means if your plus VCC is 15 volt, this will be 15. If it is 9 volt, it will be 9. And these two applications of op-amp as an open loop comparator is very important in understanding symmetry trigger circuit and so many other applications of the op-amp. Now let us proceed for here. In the rarely used op-amp open loop configuration, the device is said to be saturated when this difference inputs V1 and V2 is greater than the power supply. So power supply is suppose plus minus 15 volt. And if you apply the input difference which is greater than 15 volt, means 20 volt and 1 volt, means 19 volt is the difference and power supply is 15 volt. So that is not allowed, because in that case op-amp will be said to be into the saturation. In open loop configuration, no feedback. Open loop means what? No feedback. Output is not connected back to the input. The op-amp is always used as a comparator. So this is the important thing to be noted. Now, what is an open loop circuit and what is closed loop circuit? See here, very simple. Open loop output is not connected back to input neither directly with the help of wire or nor with any resistor. So this is the open loop. You can connect this pin directly to the ground or through RG to the ground resistor, no problem. Closed loop. Input is applied and output is fed back to with the potential divider circuit to the minus terminal. RF and RG are the potential divider circuit. So this is a closed loop. So it's a very simple. Now here, if you look at very carefully, this op amp is used as non-inverting amplifier because input is applied at non-inverting input terminal, that is plus, and output is feedback through this. Now if you replace this RF by if you say this as RF feedback resistor and RG as input resistor Rin, then equation is given as Vout is equal to 1 plus RF upon Rin into Vin. So it's already studied by you. Now again the same diagram can be shown with a different thing here. So this resistor is vertical, we'll take it horizontal and connect to the ground. So here see that resistor, instead of name RG and RF, we have taken R2 and R1. Some people say this R1, this R2, doesn't matter. This is another application which is called operational amplifier as inverting amplifier, because input is applied through input resistor R1 to the inverting input pin, that is minus pin. Non-inverting pin is directly grounded. What is the equation for this? Output is equal to minus, because it is applied to the inverting input pin, therefore output is inverted. So minus RF upon Rin. Here R2 is called as RF and R1 is called as an Rin into Vin. So like that. So you can have a gain under control. So here suppose if my input voltage is 1 volt and RF is 2 kilo ohm and Rin is 1 kilo ohm. So Vout is equal to 2 kilo ohm upon 1 kilo ohm get cancelled 2. So this ratio will come 2. So amplifier gain is 2. So like that you can control it. Now this is one more diagram which I have shown as an inverting amplifier. If you apply the sine wave as an input, then you will get inverted sine wave at the output. Here RF and Rin are the same, therefore no amplification, same output is coming. Remember that not only AC but DC voltage is also amplified by using the op-amp. So most of the time students feel that if I apply here 1 volt DC battery, will it get amplified to 2 volt? Yes, it will get amplified to 2 volt. So op-amp is used as AC amplifier as well as DC amplifier. Now there is one more application of the op-amp which you know, which is called output is directly feedback to the input. No feedback resistor. RF is not there. So RF is as good as 0 and input is applied at non-inverting input. So whenever you apply input at non-inverting input, it is used as non-inverting amplifier, but feedback resistor is 0. Therefore, if you come to this equation of here, RF is 0, therefore 0 divided by anything is 0. 1 plus 0 is 1. So Vout is equal to Vin. And in this way, you will understand that this application is unity gain, that is called buffer also. So here, if the input is 10 volt sine wave, output is also 10 volt sine wave. So Vout is equal to Vin. And in this way here, the same diagram is given over here. Output is directly connected over here. Here the signal generator sine wave is applied. If it is 1 volt, output is 1 volt. If it is 2 volt, output is 2 volt. If it is 3 volt, output is 3 volt. And that is Vout is equal to Vin. So in this way, this is the these are the applications of the op-amp. Now why the closed loop configuration is more important? Because in case of op-amp, in open loop, output of op-amp either goes to plus Vsat, that is plus VCC, that is HVL, or it will go to the minus Vsat, that is equal to minus VE, that is equal to LVL, and it depends on which input voltage is greater. V1 means inverting voltage is greater or non-inverting, and output of op-amp does not remains under control. Therefore, always 99.99% the feedback is used to control the output voltage. So in closed loop configuration, the circuit performance is stabilized and gain is controlled, and it becomes far more predictable. In closed loop, we apply a small portion of the output voltage back to the inverting input. In this way, the gain and response are then determined largely by the feedback network, means RF and RIN will play important role in identifying the gain. So like that, you can read this. Now we'll go to the one more applications of the OpAmp, which is called Zero Crossing Detector. Now it is an open loop again. You can understand that here this OpAmp is used such that at the inverting input pin we have applied a sine wave. And what is the voltage of the sine wave? Peak voltage Vp is 5 volt and minus Vp is 5 volt. Means peak to peak how much? 10 volt. Peak to peak 10 volt. Now op-amp supply is how much volt? Plus VCC 12 volt minus VE minus 12 volts here. Minus VCC minus VE minus 12 volt. Now we want to understand the working of this. You know very well, for op-amp in open loop, whenever voltage at inverting terminal is greater than voltage at non-inverting terminal, output is remaining in LVL, low voltage level, that is equal to minus VEB. Now look at this sine wave. It starts from 0 volt, goes to 5 volt and then comes to 0 volt. Means during positive half cycle, the voltage at inverting pin is above 0. Is above 0. What about non-inverting pin? It is at grounded, means 0 volt. Therefore, entire during positive half cycle, voltage at inverting pin is greater than voltage at non-inverting pin. Therefore, during positive half cycle, for entire portion of the positive half cycle, output of this op-amp remains in LVL, low voltage level, and that we have shown diagram with the help of diagram like this here. It is zero crossing detector, it is called. During positive half cycle, during positive half cycle here, the voltage at inverting pin is greater, therefore output of op-amp is in Vsat minus, means your LVL, low voltage level, that is equal to minus VE. Now let us go again to the circuit. During negative half cycle, what happens? During negative half cycle, you know, in sine wave, positive half and negative half. In negative half, the voltage goes below x-axis, means below 0, minus 2, minus 4 and minus 5. Means during negative half cycle, the voltage at inverting pin is always in minus, and voltage at non-inverting pin is permanently 0. Therefore, 0 is positive as compared to all that negative value. Therefore, it is said that during negative half cycle, the voltage at non-inverting pin, that is positive pin, is greater than voltage at inverting pin, that is negative pin. Therefore, output of op-amp will remain in HVL, that is Vsat plus. So see here, during negative half cycle, the voltage at non-inverting pin is greater than voltage at inverting pin, and output of the op-amp will remain in HVL, that is plus VCC, and that is Vsat plus. In this way, at the output of the op-amp, you will get a square wave. What you will get? Square wave. Sometime output is HVL, sometime output is LVL, depending on which voltage is greater, and accordingly, the generation of square wave will be there at the output. But remember, during positive half cycle, there is LVL here. During negative half cycle, there is HVL here, because we have applied the sine wave at negative terminal, and therefore here the frequency at of the square wave at the output is exactly equal to the frequency of the sine wave at the input. So same frequency square wave and sine wave will be there. So here we have given the details that during positive half cycle, V out is equal to minus VE equal to minus 12 volt. During negative half cycle, V out equal to plus VCC equal to plus 12 volt. Frequency of square wave at the output is equal to the frequency of sine wave at input. So all description is given over here, and this is the zero crossing detector. Now let us go to the next circuit, that is also zero crossing detector, but see here very carefully. We have applied the sine wave, same sine wave, Vp plus 5 and minus Vp minus 5. So in this way, so plus Vp plus 5 minus Vp minus 5, negative P. We have applied this sine wave at inverting input, and non-inverting input pin is grounded. So you can read this very carefully. During positive half cycle, the voltage at non-inverting input pin is always greater than the voltage at inverting pin, because inverting is 0, and here non-inverting is going from 0 to 1 volt, 2 volt, 3 volt, 5 volt, like that. Therefore, here in the beginning, the output will be in high voltage level, because voltage at non-inverting pin is greater than the voltage at inverting pin. See here. During positive half cycle, the output is in HVL, because voltage at non-inverting pin is greater than inverting, and during negative half cycle, the voltage is in LVL. So like that. In this way, here again the same thing will happen. The frequency of the square wave at the output is equal to frequency of the sine wave at the input, and these are the applications of the op-amp as an open loop, as a open loop, and as a closed loop. I have told you only one example of what non-inverting amplifier and inverting amplifier in case of a closed loop. Comparator, whenever you use the op-amp, it is used in open loop. Now we'll go to the parameters of the op-amp. The op-amp is selected on the basis of various parameters, such as number one, power supply rejection ratio, PSRR. Now suppose if you have designed the operational amplifier for output voltage 2 volt and input voltage is 1 volt, so gain is 2, and you applied the power supply as suppose plus minus 9 volt. Now, if you change the power supply plus minus 9 volt to plus minus say 12 volt, plus minus 15 volt, plus minus 18 volt, then what will be the output voltage? Will it remain same? So that is determined with the help of one parameter, and it is called power supply rejection ratio. So here it indicates that this specification is listed in decibel always. 1 volt change in the power supply will cause a 0.001 volt change in the output voltage. 1 volt change in the power supply will cause to change the output by 0.001 volt. 0.001 volt means 1 millivolt, means 1 millivolt. So this is the about power supply rejection ratio, PSRR. Second input parameter is called input resistance of the op-amp. Op-amp having two inputs, namely inverting input and non-inverting input. You may apply input only at inverting, non-inverting is grounded, or vice versa. Or you may apply the input at both the inputs, inverting as well as non-inverting. Input resistance is the resistance offered by the first block of the op-amp, and first block is what? Dual input, balance output, differential amplifier. So here it is the resistance offered by the first block of the op-amp circuit. For single input, either V1 or V2, it is the resistance between that input terminal and ground. And if both the inputs are applied, then it is the resistance between inverting input and non-inverting input of the op-amp. So normally the input resistance of op-amp is very high, and that credit goes to emitter resistor Re of the first block, and that emitter resistor is very high value resistor replaced by constant current source. So it is in mega ohm. Next parameter, or see here, the same diagram comes here. What is the input resistance? Input resistance is the resistance offered by the first block between two input terminals, and if you don't apply this with respect to ground, if it is there between this terminal and then the ground, so accordingly. So here again that input resistance will be shown here. Then output resistance, it is the resistance offered by the op-amp to the outgoing signal. It should be as low as possible, and it is in few ohm. So output resistance of the op-amp is the resistance Rout offered by the last block of the op-amp, that is called amplifier. Then next parameter is called output offset voltage. What is this parameter? When you have both inputs of the op-amp at the same voltage level, when you have both inputs of the op-amp at the same voltage level or at the ground, then output voltage of the op-amp must be 0, because difference is what? 0, and first block amplifies the difference. Differential amplifier, if the difference is 0, the amplification value is 0. But in case of op-amp, the output instead of 0, there is few millivolt present at the output, and it is said that whenever both inputs of the op-amp at the same voltage, output voltage of the op-amp should be at 0 volt, but instead of 0, it is in few millivolt, and that value of voltage is called output offset voltage. This is the amount of voltage, output offset voltage here, sorry. This is the amount of voltage present at the output when V1 is equal to V2. Ideally, it should be 0 volt, but it is in few millivolt. So like that. Then what is the input offset voltage? That is the output offset, amount of voltage present at the output when both inputs are same. Input output offset voltage is the amount of voltage required to nullify that voltage. We want to make it 0. So what we do, we keep the input at the same voltage or ground, and we connect one resistor of 10 kilo ohm here between pin number 1 and 5 of OpAmp 741. So therefore pin number 1 and 5 of the OpAmp 741 are called offset null pin. A 10 kilo ohm variable resistor is connected. Variable resistor is having 3 terminal. Any one terminal you connect to pin number 1, another terminal to pin number 5, and variable terminal to plus VCC or minus VE. Here we connect it to minus VE, it is very close over here. And in this way, by varying this pot, we can inject this negative voltage inside the op-amp, and output voltage is nullified. So here again the same diagram is shown. Pin number 2 and 3 are connected to the ground, plus VCC minus V. Pin number 1 and 5 are connected to the variable resistor of 10 kilo ohm. One terminal is here, one number, another terminal here, and variable terminal or power supply. So pin number 4 is a power supply. So that is a minus Vs. So we connected over here. So like that, it is very simple. And see here again, pin number 1 offset null, pin number 5 offset null. So in between pin number 1 and 5, what is there? Variable resistor of 10 kilo ohm standard, it is connected, and in this way offset null is there. Next parameter of the op-amp is input offset current. Input offset current. What is the input offset current? This is the difference between IB1 and IB2. Input offset current. I of IB1 and IB2. Now, actually speaking, due to very high input resistance of the op-amp, this is whatever it is shown, I10 and I20. It is for ideal op-amp, and ideal is only imaginary term. It does not exist in real life. So in real life, there is a practical op-amp, no ideal, because input resistance, even though it is very high, some current I1 and I2 flows through the op-amp in microampere. Therefore, I1 cannot be 0 and I2 cannot be 0 for applied V1 and V2. This is ideally it is shown. So input offset voltage is the difference between two. Input bias current. Input offset current is the difference between two input currents. Input bias current is the average of two base currents, IB1 plus IB2 divided by 2. So it is a very simple definition. And next definition is called common mode rejection ratio, CMRR. The name itself indicates you a lot of things. Common mode rejection ratio. Whatever common, you reject it. Whatever common, you reject it. Means suppose you applied V1 as a 1 volt and V2 as a 2 volt. How much is voltage is the common? 1 volt is common. So you reject it. So what is the difference remaining? 1 volt. So you amplify that. So that is the common mode rejection ratio. And it is the ratio of differential mode gain to the common mode gain. Differential mode gain, a gain of op-amp is always represented by capital A. D for differential mode gain, CM means common mode gain. And it is a ratio of voltage gain. Voltage gain ratio means gain of the op-amp is voltage gain V out upon V in, output voltage and input voltage. So there is no unit for gain, and like that there is no unit for CMRR also. So like that. So here V1 is a one voltage, V2 is another voltage. But if V1 and V2 are different, then op-amp is said to be used in differential mode gain. If V1 and V2 are different, then it is said to be in differential mode gain. So we'll see that. We know that differential mode gain AD is equal to V out upon VD. What is VD? VD is the difference between two input voltages. VD is the difference between two voltages. Suppose V1 is 1 volt, V2 is 0.5 volt. Then for that, what is the output voltage of the op-amp? So accordingly, that ratio is taken and it is called differential mode gain. Another logic which is used, not two different voltages, only one voltage is used at inverting and non-inverting. That is called common. Only one input. Common mode. So this is called common mode gain. In common mode gain, what is the gain? Gain is the output upon input. So V out upon VCM, common voltage. Because here you see the diagram, here is the common input. to the growth. So VCM is given by the equation V1 plus V2 divided by 2. V1 plus V2 divided by 2. Why? Because if I apply here a 10 volt, then 10 volt will also go here and 10 volt will also go here. Same voltage will go at both the point. So here common voltage VCM equal to V1 is 10 volt, V2 is again 10 volt. So 10 volt plus 10 volt divided by 2 means again 10. So that is the way of mathematical representation. So it is like that. CMRR. CMRR, when it is to be expressed, it is expressed in 20 log to the base 10 ED divided by ACM. So here connecting the inverting and non-inverting input of the op-amp together to the same voltage should cause a zero output regardless of the voltage applied to the input. But this is only in theory and CMRR is specified in dB. So common mode rejection ratio is the next parameter. The next parameter is called slew rate. Slew rate, SR. So slew rate is what? Slew rate represents the relationship between change in the output to the change in the input of the op-amp. So in case of op-amp, when we apply the input as a sine wave of particular frequency at the input, the amplified signal appears at the output, but there is the same rate or different rate of change in the output with respect to input or what. So that is represented by slew rate. It is defined as the maximum rate of change of output voltage to the change in input. Slew rate indicates how fast the output can change. Usually it is expressed in volts per microsecond. Volts per microsecond. So output is in volt and time related relationship is in microsecond. So slew rate SR is equal to dV out by dt, rate of change of output voltage, maximum rate of change of output voltage. So that is called your slew rate. Then there is one more parameter, unity gain bandwidth. Unity gain bandwidth. So in case of operational amplifier, there is always a relationship between the bandwidth and gain of the amplifier. So when bandwidth is given in megahertz, and when the bandwidth is increased, of course the gain will be decreased. And here you can read this: AV is equal to 1 means voltage gain is 1, is the point at which the op-amp can't keep with the signal and the input and output are the same voltage. So when gain is 1, the input and output are the same voltage. The highest operating frequency is called as the bandwidth. So here the direct relationship between slew rate and voltage gain AV leads to calculation for gain bandwidth product, GBW, gain bandwidth product. It can seen that having the frequency allows the circuit to have the twice the gain. So here it can seen that having the frequency allows the circuit to have twice the gain. So if I want to pass the 10 megahertz frequencies to the output, then with reference to the frequencies, the gain relationship between frequency and gain is what? The gain should be twice the frequencies. So bandwidth twice. So there is a relationship between gain and bandwidth. Thus the product of the gain and frequency is always same. The product of gain and frequency is always same. This is the gain bandwidth product. Now let us go to the parameters ideal and parameters practical. So here see. Number one, name of the parameter, then ideal value and practical parameter. So input resistance. Ideally speaking, no input current should flow for any applied voltage, means input resistance must be ideally infinite. But practically, ideally is only imaginary, does not exist in real life. Practically it is 10 mega ohm or greater than that. Output resistance should be zero, but zero resistance is not possible. Even if you take a copper, it is having a very less resistance in fraction accordingly. And this is your 50 ohm to 75 ohm. Output offset voltage, ideal value 0, but few millivolt present. Input offset voltage, so we should not require any input voltage to nullify the output, but there is output, so we require some voltage. Bandwidth infinity, bandwidth in megahertz reality. Infinity bandwidth is not possible at all. Voltage gain, infinity, because we say that the input resistance is very high, infinite voltage gain, but voltage gain is very high. Slew rate should be again very high, infinity, but it is in volts per microsecond. And in this way, this is about your operational amplifier and its basic. So today's in this lecture, we will conclude this much only, and in the next lecture, we will go to the operational amplifiers one concept, which is called your virtual ground concept and real ground concept. So thank you very much for watching this video. Thanks a lot. In the next lecture, we'll proceed for the virtual ground and real ground concept and what do we mean by VDD, VCC and other applications. So thank you once again.